Millions of people sit beside commercial jet engines every day. We treat them as routine transportation, but inside that casing is a continuous explosion contained by a few millimeters of metal. To understand the physics inside, look at this scale. The interior of a modern jet engine burns at approximately 1900 degrees Kelvin. But notice the physical components. The metal turbine blades sitting directly inside that fire have a melting point of only 1600 Kelvin. According to the basic laws of thermodynamics, a 300-degree deficit means these blades should physically liquefy mid-flight. Every time you board a commercial flight, you are trusting a machine that operates hundreds of degrees above its own structural melting point. Modern aviation relies on a physical impossibility. The math for jet propulsion was solved long before the physical world could survive it. By the 1930s, engineers like Frank Whittle had the aerodynamic equations completely mapped out. Early jet turbines pushed metal to its thermal limit. The sheer heat vaporized internal components, or warped them so severely that the engines required a complete rebuild after only 10 hours of flight. Pushing aerospace materials beyond their natural limits carried a heavy human cost. In the 1950s, the de Havilland Comet, the world's first commercial jetliner, began experiencing catastrophic failures, literally ripping apart in the sky. The culprit was metal fatigue. Investigators realized that the repeated stress of pressurization at high altitudes was forming invisible microcracks inside the aluminum and steel, eventually tearing the aircraft to pieces. Aerodynamics could only push aviation so far. Overcoming the destructive forces of heat and pressure was strictly a material science problem. To stop airplanes from disintegrating, the aerospace industry turned to the blacksmiths of the atomic age, metallurgists tasked with inventing entirely new chemistry. Standard steel was too weak, so these chemists began experimenting with nickel. They created new mixtures known as superalloys, designed to retain their strength inside an inferno. To manufacture these superalloys, they had to be forged inside vacuum induction melting furnaces. Removing the air from the process prevented oxygen and other impurities from corrupting the liquid metal as it cooled. But an engine blade faces more than just heat. It spins at thousands of revolutions per minute. Even the purest chemical mixtures struggled to withstand the rotational pulling force trying to rip the blade out of the engine. That pulling force exposed a physical weakness at the microscopic level, leading to a phenomenon known as creep rupture, where solid metal slowly stretches and deforms until it snaps. As this microscopic view illustrates, standard metal is a mosaic of tiny individual crystals packed together. Under extreme heat and centrifugal force, those boundary lines rub against each other and pull apart. The solution required manipulating how the metal cooled from a liquid to a solid. Engineers developed a process called directional solidification, which forced the metal to crystallize in a single continuous direction inside the lab. The result was the single crystal turbine blade. You are looking at a component grown from a single atomic structure, which eliminates the weak microscopic boundaries. By erasing the internal borders of the metal itself, the blade can survive the violent pulling forces of flight without tearing apart. But that brings us back to the original paradox. A single crystal nickel alloy still melts at 1600 Kelvin. The gas flowing over it is 1900 Kelvin. To bridge that 300-degree gap, engineers rely on the internal architecture of the component. The inside of the solid metal blade is hollow, filled with a maze of complex internal channels. Relatively cooler air from the front of the engine routes through these internal channels. The air is then pushed out through microscopic holes precisely drilled all over the exterior surface of the blade. This creates a constant microscopic barrier of cool air wrapping the entire component. The 1900 Kelvin exhaust gas glides over the top of the barrier, never making physical contact with the 1600 Kelvin metal. To survive an environment that physically exceeds its material limits, the engine actively defends itself. The metal is, in a very real sense, sweating to stay alive. Look at the sheer scale of a modern high-bypass turbofan engine. It is a massive piece of industrial machinery. Inside that casing, highly purified superalloys are acting as unbroken single crystal structures, forcefully sweating cold air into a 1900 Kelvin inferno, all happening simultaneously, millions of times a minute. The history of flight records the names of test pilots and designers. But the survival of the jet engine was determined by materials scientists working at the atomic level. Their ability to manage heat and molecular physics is the specific reason global commercial air travel is possible. When you board a flight today, you are relying on an exact atomic arrangement. You are riding on a material structure that survives in an environment where